Welcome. We're going to look at how to use z-scores, and we're going to start with an example like this with a bell curve. Put a dash through here, and the mean is here, which we'll call at the number 700. I'm going to say that the standard deviation is 100. That means that 100 larger than 700 will be 800, and then we'll have 900. And 1,000 way out there. And going the other direction, we're at 600, 500, and 400. Now, you know from the distribution in a bell curve that the majority of the data is between this area here. In fact, about 68% of it is there from one standard deviation away from the norm. Well, what we're going to look at, and in fact, given that, you should figure out at any one of those 100 points the percentages above or below. Well, we're going to find one that's in between. Let's go here to 850. At that particular area, what is the percent of people who are below that area? Or what is the percent of the people above that area, or the data, I should say, as opposed to people. The thing is the data. The amount of data that's below 850 or above 850. Well, when it is not a normal percentage, like we're used to 34% here and 34% here, and then it's 13.5% here and 13.5% here. So if we were knowing from, that goes to 900. From 700 to 900 would be 34 and 13.5. So that's what, 47.5%. So if we know the exact 100 number, we're set to go. But when it's in between like this, that's another matter, because now we can't apply those same percentages. We know it'll be somewhere between it, but because of this curve down here, so we know we'd be adding up all these percentages, but we can't add up the next 13.5 because 850 is in between. So let's figure out what that means in between. What is it for all of this up to there? We use this formula. We use a z-score, and this formula gives us that number, and then we use a z-score table to find the percentage. So let's look at what these are. This is your percent that you want to have, okay, or it's your, not your percent, that's the wrong phrase for it. It's your data point. In this case, the data point is 850. So I have 850 minus the mean, which is the 700 here, divided by the standard deviation. That's the symbol for standard deviation. A circle with a little hair lip kind of thing or something like that. Put 100 under it. So that equals 150 over 100, which is 1.5. Now we have to put a second decimal on it, so we have to put a 1.50. So what we now do is use 1.50 on the z-score table. Now, it's actually not officially called the z-score table, but let's look at it. I have it at the end of this document. It will all render correctly. So last couple pages. Okay. It's actually called the standard normal cumulative probability table. Normal is the bell curve. So what it starts with is negative z-scores here. And so we're looking at here at negative 3.4, and then this one gives the second decimal. So if it was negative 3.48, we go over to here, and this would be the number for it. But that's actually not the one that we're using. We are using 1.5. So we have to go past the negatives to a second page, and we have to come and find 1.5. There's 1.5. Yeah, circle in red too. Now look at the decimals above it, and we have 0, 0, 1, 2, 3, 4. We were looking at 1.50. So that means this is the column that we'll use, and we'll take that first number here. This is the one that we want, 0.9332. Let's go back and write that down. So a z-score, okay, so z-score 1.50 leads to 0.9332. Take the decimal place and move it over twice, and so what you actually have is 93.32%, or round that to 93%. So we would say 93% of the data is below 850. 93% is a lot of it. Well, the reason for that is because it's all the area below it, all the way down to the other tail. So the only part that is not included here is this part, and that ends up being about 7%. So above 850 is 7% of the data, and below 850 is 93% of the data. So let's look at another one here. This is done with a curve, but we really don't need the curve. All we really need is the formula, and we need the three numbers that go into it, and then we need the z-score table. So 4 things, and we can figure out the percent above or below. So now let's look at this one. A data set has a mean of 85.75. There we are with the mean. And standard deviation, so I'll do the little symbol here for standard deviation. What percent of the data is below 80 and above 80? So 80 is our x. So the z-score is the x minus the mean over the standard deviation. So it's 80. So it's 80 minus 85.75 divided by the standard deviation of 8. Put that into the calculator, and you get that it's equal to negative 0.71875. Remember, we only need 2 decimal places. So that means the 8 can change the 1 into a 2, negative 0.72. So my z-score here, z is equal to negative 0.72. Well, let's see what that means. If that's the z-score, let's go to the table, and negative 0.72 corresponds, well, let's go look at it. Save end here. Negative 0, here's 0.7. So there's negative 0.7, but we didn't find the 2. So coming back up here, here's the 0, the 1, and the 2 column. So we want that 2 column, so we want to go to this spot. So that's where we're going over from the negative 0.7 and coming down from the 0.02. So let's go and put that in back on page 1, 0.2358. 0.2358. Move that decimal twice, and it's 23.58%, or about 23.6%. That's harder to round because it's pretty much in the middle. I think here the 0.6 is appropriate. So what we would say is 1 below 80 is 23.6%, and 2 above 80, well, that will be the difference from 100. So over here, I'll calculate 100 minus 23.6, which is about 76.4, or is exactly 76.4%. And those are our two answers then, for 1 and 2. Okay. Let's take a look at the second page now. In a group of teenagers, average height is 150 centimeters, standard deviation of 20 centimeters. So the average, so that's the mean, standard deviation, that's the 20. Darnell's height is this much. What percentage are shorter or taller than Darnell? Well, that means this is our X. So we can simply do a z-score of the X minus the mean over the standard deviation. So 161.4 for X minus 150, okay, and over the standard deviation of 20. Okay. So that comes to 0.57. So let's go to the table for that. Okay, so 0.57. Okay, down here, the zeros without decimals, 0.5. And now we need a 7. Here it is. So this one comes along to here. And this one would have come down here, but wanted to be sure about it. Now, 7156. 7157. So the table comes out to 71.57. So that 7 could really round that to make it a 6. 71.6. And that's what we'll work with. Well, that's the ones that are shorter. So shorter is 71.6%. And taller would be the opposite. So 100 minus 71.6 would be 28.4. Okay. And so now we know those answers. Shorter than Darnell or taller than Darnell. Oops. Supposed to be an outline. Okay. Let's go on to example 3. Set of exam scores have a mean of 80, standard deviation of 6. 1 person scores 75, and then below or above, same thing as before. In fact, this is a good one to practice. You can, if you want to, stop the video, figure out this problem, and then come back and see if you're right, because I'll start doing it. Okay, welcome back. Let's use the z-score formula where it's the X, which is 75, minus the average, 80, divided by the standard deviation of 6. Okay, so that comes to negative 5 over 6, which is actually negative 0.8333. We don't need all those 3's. This one doesn't round that one, so they go away because we can only do two numbers in the problem, or 2 decimal places all we need. So let's go to the z-score table, and negative 0.83 corresponds to 0.2033. So let's go double check that, negative 0.83. Negative 0.8 first. That one's right here. And then a 3. Well, let's see, it looks like the 3's have to be this one here. Okay, so what we get, oops, I went down too many. I am on this one because this one comes over to here, and then we're in the right column. So what it is I have to make sure I can still see it. 0.2033. So let's go back up and write that. And that's what it comes to. We see it now. That's what I had there. Move the decimal twice, 20.33%. Well, that's low enough that we can just say 20%, approximately 20%. So 20% scores are below. Scores are below 75. 80% scores above 75. Now, let's come over to a different type of problem. We're going to find the area between two percentages. So here's an example. My height, about 59.5, 5'9", 5'9", which in inches alone is 69.5. My son's height is 5'6.25". Now, actually, I set this up with the son in mind a couple of years ago, and that was indeed his height. However, he's now a little taller, but not that much. He's about 5'6.75". So this is still a good example, and I'm just going to keep this one. In a normal distribution, adult males have an average height of 5'10". We're going to call that, then we're going to keep it by inches, and that's the mean, and a standard deviation of 2¼ inches. What percent of adult males, American adult males' heights are between me and my son? Okay, look at this in terms of a bell curve. In fact, bell curve doesn't go below the line ever. So the mean here is 70, okay, and 2¼ So if I go up, that's 72.25. If I go down, this is 67.75. Yeah, let's see if I get that right. Down 2 and down 1/4. Up 2 and up 1/4. I believe that looks about right there. Okay. So what's happening is my height, whoops, get that back there. Uh-oh, don't mean for it to freeze. Good, there it is. My height is just below the 70. His height is a little bit below even the 1 standard deviation. So we want to know what percent is in between here. It's not one of those exact numbers of 34% or 13.5, because those are only for the actual 1 full standard deviation or 2 full standard deviations away, and this is in between. So what we'll do is we'll figure out one of them, like all of this, mine, and then we'll figure out the second one there, his, and subtract it. So just one of the percentages, subtract the other. So let's start with me. The z-score is equal to 69.5 minus 70 over 2.25, which comes to approximately negative 0.222, and so on. Now that's enough to simply say, oh, negative 0.22 is good enough as a z-score. His, my son, is 66.25 minus the 70 over 2.25, which comes to approximately negative 1.6. And that 6 is repeating. So if I keep going like that, this 6 will make that one into a 7. Okay, so there's that one. So the two z-scores, let's go to the table, or we've done it a couple of times. So now let's use this. The table for negative 0.22, that is 0.4129. So that would be about 41%, 41.3%. I'll move that over twice. Yeah, we call it that, 41.3%. So that's for that number. For the other one, negative 1.67, that gives the actual percentage is 0.0475. Move the decimal over and it's 4.75%. Oh, so and that's a very small percent. So because of this curve coming down, this is not a very big amount here. It looks big because of my drawing, but it's probably more of a curve like this. So now what we'll do is subtract them with the area that's here. 41.3 or 0, subtract 4.75. Done. 41.3 subtract 4.75, get the exact amount here, is 36.55. So right about in the middle there. So that means 36.5 or around that, 5 up, 36.6% of American males' heights are between his and mine, which is 66.25 inches, and 69. I have 69 exactly, 69.5 inches. Okay, and there we have that answer. So that's a little more than a third of American males' heights are between my son and me. Now, this next example is a nice, interesting one. A company is planning on closing the stores with the lowest profit last year and enlarging the stores that had the most profit. The company decided all the stores with profit last year below that will be closed, and if they're above it, then they'll get enlarged. So the company is using a normal distribution with a mean of that. That's our mean, and a standard deviation of $200,000. What percentage of stores will not be affected? Well, let's look at what this means. We don't have to do something like this in a graph, just like I didn't have to do the last one that I had set up either. However, I like to see it in a way what it means. So it would be something like this. The basic idea, some of them, the top ones are getting enlarged, the bottom ones are being closed, and so what all this area in between here, all those stores, what is that percentage? And so here's how we'll do that with this one. We're going to find z-scores for those numbers, find out what percent this is and what percent this is, and just subtract them from 100. Or actually, we could find all of this one and then subtract this one from it. That's probably where we're going to go here. So first, closing. The ones that are closing have this z. They're 290, the amount, 295,000 minus the mean, 550. Okay, 550, I think it's an extra 5000. 4 zeros. Okay, good. So 295 minus 550 over the standard deviation of the 200,000. Okay, you've got all those numbers in there now. And that's equal to negative 1.275, which will round to negative 1.28. When I go to the table for that, and I'll do it right here now, the table for that number gives me a percentage of 0.1003. Can't round that, so it's a 10%. Now, let's do enlarging. The z-score for that is going to be the 740,000 minus the 550 So let's make this a much better number. Over the 200,000. And since I'm sort of out of room there, we'll continue down here. That gives me a Z of about 0.95. And in the table for that one, that's 0.8289. Move the decimal twice. The 9 makes the 8 a 9. That makes that a 3. That looks like what? 83%. Okay. So this amount up to here is 80. Stop going away on these. 83%. And this amount here is 10%. So we just subtract 83 from 10. 83% minus 10%. So it gives us 73% of the stores are not affected. So it looks like 10% were affected being closed, 10% of the stores, and 17% above the 83 were being enlarged. They're doing pretty well. Okay. So let's go to the last page with different type of thing, where we're going to sort of go backwards on here. Distribution of SAT scores in a past year, approximately normal, with a mean of 1483 and a standard deviation of 318. A summer program only accepts students in the top 10%. What score is needed? So we can figure out something here, but let's talk over a way of looking at this. The mean, and the top 10% will be, say, over here, 10%. But when we do the z-score table, let's do there. The z-score table gives you a percentage that is below a number. So we have two choices here. One of them is to find the 90% amount to find the number, or we do the 10% amount, but then switch it, do the opposite of it. So I'll show you what I mean. I'm going to go ahead with the 10% and work it out with that. So the z-score is equal to x minus x with a, or x, the mean, over the standard deviation. So that's equal to, well, actually what we think here is what we need to do is figure out for 10% what is the z-score. So we've got to go into it, or the 90%. So let's go take a look at that and think about either the 10 or the 90 and think about what that number should be here. So we're going to come down here to this, and we're going to look up. Now here's a 10, 0.01, 0.1 is our 10%. Okay, and this looks like the best number. So that one comes over here to negative 1.2 and the 0.8. So we're looking here at a negative 1.28. Now let's go to where it's 90%. And look for where it's 0.90, as close as possible to a straight 0.90. Okay, and what I see here is 0.9, 0.915, and it looks like this one is the closest number, 0.8997, would round to 90 more than this one or that one. And that one, oh, look at that, 1.2, and above here is the 0.8. So the number there is 1.28. So we have positive 1.28 or negative 1.28. So in this case, it makes more sense to think of it as the positive 1.28. We could go with the negative, but actually, well, let's go through and see what happens. The z-score, therefore, is 1.28, so I'm going to use that positive one. So it's to get up to this level here. Part of it is the negative 1.28 in reality is down here. So if I did negative 1.28 z-score, it would be this amount down here, which is not what we want. We're looking for up here. And so we need to get to this place. So 1.28 is equal to x minus, we need this x here, minus the mean is 1483 over the 318. So just to show here, 10% change to 90% gives us that. So now I'll continue. All we have here is solving for x. So we multiply by 318 on both sides. We get 407.04 is equal to x minus 1483. In this case, 0.04 is definitely exceeds. We don't really need that amount. But we'll add 1483 to both sides. We'll keep it as integers rounded there. And that means we have x alone. And I'll bring that to here, that x is equal to 1890 when we add these together. I think I need to write down that number more clearly. We're adding 1483 on both sides. And that gives us an 1890, and that's what the score is, because what x here was the score that we needed, subtract the average, divided by the standard deviation, and it turns out that the score for 10% is, for the top 10%, is 1890. And that's how you work it out. We're thinking about very carefully about which ones of these you should have and being able to solve for the x rather than solve for the z-score this time. Here's another type of one, the distribution of reading scores, fourth grade, approximately normal, with a mean of 312, standard deviation of 41. So researchers, intervention program, student must have a reading score in the lower 40% for their grade level. So it's looking like this. Say 40% is here and they need to be here. So we're not worried about this time about picking the top one. We need this one. So that means we will go looking in the z-score for 0.4000, as close as possible to that. And then whatever z-score that is, we'll be doing z equals the x that we want. So we need that that reading score minus the average divided by the standard deviation. So we already have this and we already have this. We're about to get this one through using the 0.4000 or 40% to get the z-score, and then we'll be able to solve for the x. So let's go looking for 0.400. There's 0.12. Here's some 4s and 4.2, 4.1. So the lowest 4 seems to be, or the one closest. So we have 3974.4013. This one is 13.0013 away from 40%. This one would be 26.0026 away. That makes this one closest to 40%. So over here, it's negative 0.2. And up here in this column, it's a 5. So negative 0.25 is what we're looking for. Okay, 2 or 3. Okay. So we're looking at negative 0.25. Let's come up here for that. Just double check my number. 0.4. Ruler wise, for some reason my eye's having a problem with that one. Yeah, no, that's right. Negative 0.2. That looks good to me. And then it's the 5, negative 0.25. So we're now going to put negative 0.25. That was the z-score for the x that we want, minus the mean is 312 divided by the standard deviation of 41. So now we're going to multiply 41 times negative 0.25, and that gives us negative 10.25 equals x minus 312. We'll add 312, and x is equal to 301.75. So that we can round to 302. That's what I'd suggest here. So that means that students need a score of 302. Students with a score of 302 or less will be accepted into the program, will be in the program. Good enough there, in the intervention program. And that would be our answer, is 302. All right. Or approximately 300. But if they want to keep to the exact number of 302, or that would probably be best on there. So hopefully this helps, having seen how to use the z-score table, how to use it to solve some things, all these problems in between. So what we have, let's go back and review the concept here. Is the z-score is helps you find the percentages below a certain place. And here is without a scenario, but given a mean and a standard deviation, you can find the z-score and then find percents of data above or below whatever number you pick. Right? Here is one with height, exam scores, another one with height. It's actually, these problems are really good ones for picking, knowing below and above, and how to use that little formula. So you'll want to make sure you memorize that formula, the z-score formula. All right, and good deal of things to have done. Hopefully this helps. Thank you for watching and listening.